If your mind will not power down, borrow a star's rhythm. It can shine for 10 billion years. Tonight we drift through star birth and steady light. Later, how calcium in your bones began as starlight. If you are still awake, tap subscribe once, dim your screen, set a sleep timer, and then stop touching the phone. Just listen and let everything stay still. Settle in and let the room be quiet around you. Imagine the night sky as a slow map, not a puzzle to solve. If your thoughts feel busy, we can give them something wide and steady to rest on. Are you picturing a clear sky or a cloudy one? Either way is fine because the tour happens gently in your mind. Start with one simple idea. Distance can be soothing. The nearest star after our sun is only a few light years away. A light year is not a time. A light year is a distance. The length light travels in 1 year. Light moves quickly, but space is still spacious. So even nearby stars are far in a quiet, patient way. Picture a soft beam leaving a star and gliding through darkness for years. It does not hurry, and it does not struggle. It simply travels like a calm message in a bottle. If you have been carrying urgency today, you can set it down here. Nothing to do. Just listen. Now widen the view as if you are slowly pulling back from the Earth. First you leave your street, then your city, then your continent. From far away, the Earth becomes a small, dim marble of cloud and ocean. The moon becomes a companion dot, circling with steady timing. Then the planets spread out like quiet stepping stones around the sun. The sun sits in the middle, warm and ordinary in the best way. In this part of space, ordinary still means immense and bright. Now pull back farther beyond the outer planets into a colder, darker reach. The sun becomes one star among many, no longer the center of everything. That shift can feel calming, like loosening a tight grip, because when your view gets larger, your worries get smaller. Not because they do not matter, but because they do not have to shout. A few light years becomes a neighborhood in a much larger city. Nothing to do. Just listen. Let's name one more gentle scale. Our home galaxy, the Milky Way, stretches about 100,000 light years across. That number is so large that it does not need to feel real tonight. You can treat it like a soft horizon, a calm boundary. A light year is a way of saying space is wide and time has room. If you like comparisons, imagine the Milky Way as a long, quiet road of stars. From one end to the other, light could travel for many thousands of years. And yet, the galaxy is only one home among many. Even that idea can be held softly without any pressure. Now, for a moment, picture yourself under a dark sky. Not a perfect sky, just a simple one with a few visible stars. Choose one star in your mind and let your attention rest there. It is okay if the image fades in and out. You are not trying to see sharply, only to drift. Nothing to do. Just listen. As you look at that star, you may notice it seems to shimmer. That gentle shimmer has a quiet cause close to home. Our atmosphere is not still. It has layers of air that are slightly different in temperature and density. As starlight passes through, those layers bend it a little this way and that. The bending is small, but your eyes are sensitive to it. Because a star is so far away, it looks like a single point of light. So even tiny changes in the air can make it seem to flicker. It is not the star struggling. It is the air, softly moving like a slow current in water. You can imagine the light as a thin thread, gently wiggled as it arrives. Even with that wobble, the light still reaches you. It still completes its long trip and lands on your eyes. Nothing to do. Just listen. Now think about planets for a moment. To the eye, planets often look steadier than stars. That is because a planet is not a single point of light. A planet shows a tiny disk, a small shape spread out across your vision, so the atmosphere's bending averages out more smoothly. The planet keeps a calmer glow even when the air is restless. If you have ever watched Venus low in the sky, you may have seen it sparkle. Closer to the horizon, the air path is longer, and the bending is stronger. But high overhead, things often look steadier and quieter. You do not need to test any of this tonight. Just let the idea sit like a soft explanation in the background. In this story, even twinkling has a gentle reason. Nothing to do. Just listen. Now we can return to the widest view, the Milky Way itself. The Milky Way is a spiral galaxy, like a slow pinwheel made of stars. Spiral does not mean fast. It means a graceful shape, turning over very long times. Imagine a calm city seen from above at night, with many lights spread through neighborhoods. Some regions are crowded, some are quieter, and all of it moves slowly together. Our sun lives in one of the quieter neighborhoods. It is not in the busy center. It is out in a calmer orbit, partway from the middle to the edge. You can picture it as a suburban street in a very large town. The sun circles the galaxy with patience. One full orbit takes hundreds of millions of years. That kind of time scale can feel like a deep exhale, because it reminds you that nature has rhythms that do not rush. Nothing to do. Just listen. If you have ever seen the Milky Way as a pale band across the sky, that is our view from inside. We are looking through the disk of our own galaxy. We see many distant stars layered along the line of sight. To the eye, it becomes a soft river of light, a faint glow like mist. In photographs, it can look bold, but in real life, it is often subtle and shy. And that subtlety matches tonight's pace. Quiet glow, not a bright demand. Now, keep a small open loop in the back of your mind. Much later, we will come back to what happens when the sun grows older. For now, we just place that thought gently on a shelf. There is no urgency in it, only curiosity. You can fall asleep before we return, and the story still works. Nothing to do. Just listen. As you picture the Milky Way, notice how it gives you an address. Not a street name, not a number, just a sense of where you belong. A small planet around a steady star, inside a slow spiral home. When your mind runs, it often stays close to the ground. Tonight we let it stretch upward and then soften. We will keep things simple with rounded numbers and calm descriptions. No sharp turns, no rushing, no need to remember every detail. Just a steady drift through real facts, held gently. And with this wide, quiet scale in mind, we can move to the places where stars begin. Next, we will drift into nebulae, the quiet cradles of starlight. Now we drift into nebulae, the quiet cradles where stars begin. Imagine a dark, cool cloud like velvet in the shape of space. It is not loud or fiery. It is patient, wide, and barely there. A nebula is a cloud of gas and dust spread thin across an enormous volume. It can be so large that light would take years to cross it. And yet, if you could float inside it, it would feel almost empty. The atoms and molecules are far apart, like a faint perfume in a vast room. Still, over time, even a thin cloud can gather into something real. In star-forming regions, the cloud is often called a molecular cloud. That simply means much of the hydrogen is paired into molecules. Hydrogen molecules like the cold. They hold together best when the cloud stays chilled. These nurseries are some of the coldest places where matter can still change shape. A typical star-forming cloud can be around 10 Kelvin. That is only a few degrees above absolute zero. Cold might sound lifeless, but here it is helpful. Cold means the gas moves more slowly, and slower motion makes it easier for gravity to do its quiet work. Think of warmth as a gentle stirring that pushes material apart. Think of cold as a stillness that lets material settle together. In a cloud, gravity is always pulling inward. Gas pressure, created by motion, is always pushing outward. Star birth begins as a slow negotiation between those two tendencies. Nothing to do. Just listen. You might wonder what keeps a cloud cold for so long. One important helper is dust. Dust in space is not like household dust. It is made of tiny grains, often smaller than smoke particles. Some grains are silicates, some are carbon-rich, and many wear thin coats of ice. They are small, but they matter. Dust grains can block harsh starlight and create gentle shadows inside a cloud. Those shadows protect the interior from warming. Dust also helps the cloud cool by letting it radiate energy away. In a simple way, dust is a quiet thermostat. It helps the cloud stay dim and cold. And in that cold, gravity has time to gather material. If you are picturing a bright, colorful nebula, that is one kind of view. Some nebulae glow when nearby stars shine on them. But the star nurseries themselves can be dark and hidden. They are sometimes seen as silhouettes against brighter backgrounds. Dark lanes in the Milky Way are often dust-rich clouds, quietly in the way. So tonight, picture a nursery as mostly shadow with soft edges, a calm darkness with structure inside it. Nothing to do. Just listen. Inside a molecular cloud, the gas is not perfectly smooth. It has knots and ripples. Some parts are slightly denser than others. Those small differences are important because gravity pays extra attention to density. Where a region is a little denser, it pulls in more material. And as it pulls in more material, it becomes denser still. This is how a cloud begins to fold inward, almost like slow fabric. Astronomers have a simple idea for when collapse can begin. It is often called the Jeans idea, named after an early researcher. In plain language, it says this: if a pocket of gas becomes dense enough and cool enough, it can no longer hold itself up. The outward push of pressure is not quite enough, so the pocket starts to shrink. Not suddenly, but gradually. A slow inward drift that can take a very long time. You do not need the math tonight. Just keep the image of a cloud deciding to gather itself. A quiet choice made by gravity over many thousands of years. Nothing to do, just listen. There is another gentle truth here. Even when a region begins to collapse, it does not collapse all at once. It often breaks into smaller pieces. Each piece can become a separate core, and each core can become a separate star. That is why stars are often born in groups, not as a crowd in a hurry, but as neighbors forming in the same neighborhood. Some will be small and long-lived. Some may grow larger and burn faster later on. But at the beginning, they share the same quiet cradle. Now, what makes a calm cloud start folding more strongly in one place than another? Sometimes nothing dramatic is required. A cloud can slowly drift and compress in the gentle tides of the galaxy. But sometimes a small nudge helps. A passing wave of pressure can move through the gas. It might come from nearby star formation. It might come from a distant explosion long ago. It might come from two clouds brushing past each other and compressing at the boundary. These are triggers, but we can hold them softly. They are not sudden blasts in your mind tonight. They are slow motions, like a swell passing under a boat. The wave squeezes parts of the cloud slightly tighter. And that squeeze can be enough for gravity to take over in a dense pocket. Nothing to do. Just listen. As collapse begins, the cloud core becomes a place with an inside and an outside. The outside is still very cold and diffuse. The inside becomes denser and more shielded. At first, the core stays cold because it can still let energy escape. But as it densifies, it starts trapping more of its own warmth. This is a key rhythm in star formation. Cold helps collapse begin, and later, density helps warmth build. Warmth does not start as fire. It starts as pressure and gentle heating from compression, like slowly squeezing a pillow and feeling it get a little warmer. This warming happens because gravity turns motion into heat. Particles fall inward, gain speed, and bump more often. Those bumps share energy, so the core warms bit by bit. In about 10 minutes, we will reach the moment a star truly switches on. For now, we stay in the nursery before that moment arrives. Nothing to do. Just listen. Let's look at the architecture inside these clouds. Star nurseries are not smooth spheres. They are often threaded with filaments, long, faint strands of gas and dust, like rivers seen from above. Along a filament, matter can flow and pile up. Where several filaments meet, density can become higher. Those meeting points can turn into cores. It is a quiet kind of plumbing. Not metal pipes, but gravity-guided pathways through cold gas. If you imagine velvet, imagine it with faint seams and folds. Each fold is a place where material likes to collect. When telescopes map these regions, they often see that pattern again and again. Filaments, knots, and sheltered pockets. It is orderly, but not rigid. Like wind shaping sand into long, soft dunes. Nothing to do. Just listen. You may also have seen images of tall pillars inside nebulae. They look like columns or cliffs in space. Those shapes form at the edges of clouds. A nearby bright star can shine on the cloud surface. Over time, light and gentle winds from stars can erode the less dense material. Denser parts resist longer, so the edge becomes sculpted into fingers and pillars. The tips can shelter small, dense globules. Inside those sheltered tips, new stars may be forming out of sight. The pillars are not rushing forward. They are being slowly carved back, like stone weathering in very slow motion. It is a calm kind of shaping. Light presses, gas flows, edges soften, and time does the rest. If that picture feels too vivid, you can simplify it. Just imagine a cloud with a softly lit boundary and a darker interior. Nothing to do. Just listen. Now, a small open loop to keep your mind gently engaged. The same dust that hides newborn stars also helps build future planets. We will return to that later when we talk about disks and leftovers. For now, just hold the thought that dust is both curtain and seed. It blocks light, and it also provides material. In a young system, dust grains can stick together. They can grow from tiny grains into larger clumps over time. That slow growth is part of how planets begin. But tonight, we are not there yet. We are still in the cloud, where dust is mostly a cooling shade and a soft shadow. Let's continue deeper into the nursery. Inside the densest regions, the cloud becomes almost like a womb of darkness. Visible light cannot travel far through it, so the earliest stages are hidden from normal sight. This is one reason astronomers use infrared and radio observations. Those wavelengths can pass through dust more easily. You do not need the instruments tonight. Just remember the mood: hidden, quiet, and slow. Star formation is not a flash. It is a long, steady gathering. Nothing to do. Just listen. Now we approach a turning point. Collapse into a core that begins to spin. Almost everything in space has a little motion. A cloud is not perfectly still. One part drifts one way, another part drifts another way. These tiny motions are gentle and random at first, but as gravity pulls material inward, the motions add up. When a region shrinks, any small twist becomes more noticeable. It is like drawing your arms in while you slowly turn in a chair. The turning can feel a little faster, even if nothing new is pushing you. In physics, this is linked to conserving angular momentum. But we can keep it simple. When collapse concentrates material, it also concentrates rotation. So a spinning core is a natural result, not an exception. Most newborn stars begin with at least a slight spin. Nothing to do. Just listen. As the core contracts and spins, it begins to flatten. Not into a perfect disk right away, but into a shape with a preference. Rotation makes it harder for material to fall straight into the center from every direction. Instead, some material settles into an orbiting plane. This forms a rotating disk around the central core. Think of a slow whirlpool, but made of dust and gas, not water. Or think of a wide vinyl record, softly turning in darkness. The disk is a natural way for the system to organize its motion. It is patient and stable. It also becomes the place where later worlds may grow. And the center, still hidden, continues to gather mass. This is the path from cloud core to protostar. We will step into that next. Nothing to do. Just listen. Before we leave the nebula, notice how gentle the whole story is. A cold cloud cools a little more. A dense pocket gathers a little faster. A filament feeds a knot. A shadow shelters a core. A tiny spin becomes a disk. This is how stars begin to assemble themselves. No one moment needs to be sharp or startling. Even the idea of a trigger can be held like a distant ripple. If your mind wants something to do, let it picture the cloud again. Dark velvet, soft filaments, a slow inward fold. Now and then, a quiet rotation beginning, and somewhere inside, a central warmth that is still unseen. Later, we will connect these beginnings to the elements we care about, like carbon and oxygen. For now, it is enough to know the nursery is already preparing the stage. Dust cools the cloud, and dust will later help form worlds. Gas gathers, and gas will later feed the young star. Everything is recycling itself in a calm loop. Now we can move one step closer. From a nebula's quiet density, the next step is a protostar, warmth beginning, still hidden. Before we go on, a tiny optional pause. If this is helping, you can save this video to a sleep playlist right now. Just one small tap, and then let your hands rest again. No searching, no scrolling, no extra choices. If you are already drifting, do nothing at all. You are not missing anything. The story will keep moving at the same gentle pace. And if you listen to this again on another night, your brain may start to treat it like a familiar signal. A calm routine. A quiet path back to sleep. So save it if you want, or simply stay exactly where you are, breathing slowly, letting the details fade into the background. Either way, you are doing it right. All right, back to the story. Our cloud has a warm center now, a protostar taking shape. Our cloud has a warm center now, still wrapped in dust. This is the protostar stage, a star in the making. It has not switched on with fusion yet, but it is already becoming warmer, denser, and more organized. Protostars are powered mostly by falling in. Gravity pulls material inward, and that slow fall releases energy as heat. It is like a long, quiet compression. Nothing dramatic, just a steady warming. The timescales are roomy. Depending on how much mass is gathering, this stage can last from tens of thousands of years to a few million years. Tonight, you can treat that range as one idea. It takes time. Space is patient. And star birth is mostly a story of patience. If you picture the core, imagine a small warm ember hidden inside a thick blanket. The blanket is the surrounding gas and dust. The ember grows slowly as more material arrives, and the blanket keeps it concealed from ordinary light. So the earliest star is more felt than seen. We often study protostars in infrared and radio light because those wavelengths slip through dust more easily. But you do not need the instruments here. You only need the mood, hidden warmth growing in a dark cradle. Is your breathing slower than it was 5 minutes ago? No need to answer. Just notice and let the noticing fade. Now, around the protostar, the rotating disk continues to matter. The disk is not decoration. It is the delivery route. Gas and dust orbit in a flat plane, and over time, some of it spirals inward. This inward drift is called accretion. Accretion is not a sudden pour. It is slow feeding, a patient river moving toward a quiet lake. Material in the disk rubs against nearby material. That gentle friction helps it lose some orbital energy. And with less energy, it can drift inward. Little by little, the protostar gains mass. And little by little, the center grows hotter and more compact. Even before fusion, this growth can make the young star shine in its own way. Not like a full star yet, but as a warm source in the dark. The glow is often strongest in infrared, like heat light. This is why protostars can be described as hidden lanterns inside their clouds. Still, what you see in pictures is often the surrounding dust, lit softly from within. The real center remains tucked away. Accretion can be smooth for a while, then uneven. Clouds are clumpy. Disks are not perfectly even. Sometimes more material falls in at once. like a thicker stream joining a river. Sometimes the flow slows and the protostar rests in a quieter phase. These changes do not need to feel like jolts. They are gentle variations spread across long times. A slow swell, then a calm trough. Astronomers infer this uneven feeding by watching how brightness changes over months and years. Compared to the star's lifetime, that is like watching a candle flicker. But the main point is simple. A protostar grows by eating from its disk, and it does so in a calm, uneven rhythm. If you like imagery, imagine dust grains and gas molecules traveling in loops. Each loop is an orbit. Over many orbits, some material drifts inward. It spirals like a slow whirlpool. It does not fall straight down. It follows curved paths guided by gravity and the disk's rotation, and as it spirals inward, it carries angular momentum, the spinningness of the system. This is where the story gets quietly clever. A star cannot simply keep all the spin it starts with. If everything collapsed into the center without adjustment, the rotation would become too strong. So nature finds a way to share that spin outward. One of the ways is through jets and outflows. Jets sound intense, but we can describe them gently. They are narrow streams of gas flowing away from the young star. They often emerge along the system's rotation axis above and below the disk. Instead of a disk-shaped flow, they are like two calm, focused fountains. They are guided by magnetic fields. Magnetic fields thread through the disk and the inner region like invisible lines. Gas, because it carries charged particles, can follow those lines. So the outflow becomes channeled, not wild, but directed, steady, flowing, and surprisingly elegant. These jets can travel far, carving slim cavities through the surrounding cloud. As they move, they can make soft shock fronts where they meet denser material. We will not dwell on that sharpness tonight. We can simply say they stir the environment gently and make room. They also help by carrying away angular momentum. Think of it as the system exhaling spin so the center can keep forming. Some material leaves so the rest can settle more comfortably. It is a balancing act, and it happens in a quiet, ongoing way during the protostar stage. When astronomers observe these outflows, they often see long, narrow features in radio and infrared maps. Again, you do not need the technical details. Just the picture: a warm, hidden center, a rotating disk, and two steady streams breathing outward. Disk feeding in, jets flowing out, a calm circulation, like a slow heartbeat of gas. This balance also shapes the disk. As some material is removed and some is accreted, the disk changes over time. It can thin out. It can develop rings or clumps. And the dust within it can begin to stick together in small ways. We will return later to how disks become the birthplace of planets. For now, keep it simple. The disk is the protostar's pantry, and the jets are the system's way of staying orderly while it grows. Now, as accretion continues, the center becomes more compact. Gravity keeps squeezing. Pressure begins to respond. This is the approach toward a major milestone: hydrostatic equilibrium. That phrase sounds heavy, but the idea is gentle. It means balance. In a mature star, gravity pulls inward and pressure pushes outward. When those two are matched, the star holds a stable size. It does not collapse, and it does not puff away. It simply rests in a long-lived middle state. Protostars are not fully in that steady balance yet, but they start to find it. As the core grows denser and hotter, pressure builds. At first, that pressure comes from hot gas. Later, in many stars, pressure will be supported by energy from fusion. But even before fusion, the growing heat and density begin to create a more defined center. The protostar is learning its shape. It is learning to be a star. You can imagine it as a sphere that is gradually becoming more self-supported. Not yet complete, but more stable than the original cloud core. Now and then, the protostar can be surrounded by a cocoon called an envelope. This is a thicker region of gas around the disk and core. Some of that envelope continues to feed the disk. Some may be pushed away by outflows. Over time, the envelope thins. The system becomes less hidden. This is part of why the protostar stage is temporary. It is a transition from cloud to star, a slow unveiling. And as the envelope clears, the young object becomes easier to detect. But inside, the deepest change is still ahead. The core temperature keeps rising. Because as material falls in, it releases gravitational energy. That energy becomes heat. And the heat moves the protostar closer to the threshold where fusion can begin. Fusion is not a switch you flip with a finger. It is a condition that becomes true when the center is hot and dense enough. When particles collide often enough, and with enough energy, they can join. For hydrogen, that joining begins the long, steady chapter of a star's life. We will arrive at that soon, but we can take our time getting there. If you are sleepy, you can let these ideas blur slightly. Warm core, feeding disk, gentle jets, slow approach to balance. That is enough. Now, another quiet check-in. Is your jaw unclenched? No need to answer. If it is, it can soften. If it is not, it can stay as it is. Nothing to do. Just listen. As the protostar approaches hydrostatic equilibrium, its behavior becomes more predictable. It becomes less like a collapsing cloud and more like a stable object. Gravity still pulls in. Pressure pushes out more reliably. The star-to-be is finding a calm middle. This middle is the foundation of a long stellar life. Because once a star achieves stable balance, it can shine for millions to billions of years. That steadiness is one reason stars make good bedtime companions. They are slow machines. They operate on timescales that dwarf our worries. Now, keep an open loop gently in mind. Once the core reaches the right temperature, fusion begins, and the pace becomes very steady. That steady phase is called the main sequence. It is the long middle, the restful span where a star spends most of its life. When a star reaches it, the story becomes calmer, not more intense. The protostar stage is already calm, but it still has change. The main sequence is calmer still, because it is balance sustained. We will go there next. Before we transition, let's hold the protostar in one final image. A small, warm sphere hidden inside dust. A flat rotating disk feeding it slowly. Two narrow streams flowing outward, guided and steady. Gravity and pressure negotiating, gradually agreeing on a stable shape. This is how a star gathers itself, not by force, but by patience. Now we reach the long, restful middle of a star's life, the main sequence. Now we arrive at the long, steady middle of a star's life. This is called the main sequence. It is not a special event. It is a long period of quiet consistency. Most stars spend most of their lives here. They shine, they balance, and they change only slowly. If you like one calm picture, imagine a candle that never flickers. Not because it is frozen, but because it is self-correcting. Our sun is a comfortable example. It is about 4.5 billion years old, and it will remain in this steady phase for a long time yet. The main sequence is where a star spends its working years. It quietly turns hydrogen into helium in its core. That process releases energy. That energy becomes the light and warmth that travel outward. But the most important idea is balance. Gravity pulls inward. Pressure pushes outward. Balance found. You can let that line repeat in your mind like a soft metronome. Gravity in, pressure out, balance found. Stars on the main sequence are stable because they regulate themselves. They behave like a natural thermostat. Not a thermostat with buttons, but one built from physics. Here's how that works gently. If the core becomes a little hotter, fusion speeds up slightly. More fusion means more energy. More energy means more pressure in the core. That pressure makes the core expand a little. Expansion cools the core, and the fusion slows back toward its usual pace. The star returns to balance. Gravity in, pressure out, balance found. And it works the other way too. If the core cools a little, fusion slows a little. With less pressure, Gravity tightens its grip. The core contracts slightly. Contraction warms the core back up. Fusion resumes at its steady rate. This feedback loop is one reason stars can shine for millions or billions of years. They are not constantly on the edge of collapse. They are settled into a calm middle. If you are listening in bed, that steadiness can be soothing. It is a reminder that not everything has to change quickly. Some systems correct themselves without drama. Gravity in, pressure out, balance found. Now, to understand the main sequence, it helps to have a simple map. Astronomers often use something called the Hertzsprung-Russell diagram. We can keep it very gentle. It is a chart that compares brightness and temperature. On one side, you can imagine hotter stars. On the other side, cooler ones. And you can imagine brighter stars up high, dimmer stars down low. Most stars sit along a broad band on that chart. That band is the main sequence. Stars of different masses occupy different parts of it. But the shared idea is that they are steadily fusing hydrogen in their cores. They are stable, predictable, and long-lived. You do not need to see the chart to use it. Just picture it as a simple atlas of starlight, a quiet way to organize the sky. Now, we can move from the idea of balance to the journey of energy. A star makes energy deep in its center, but the surface we see is far away from that center. So how does the energy travel outward? There are two main styles of transport inside many stars. One is radiation. The other is convection. Radiation here does not mean anything alarming. It simply means energy carried by light, by photons. In a dense star, photons do not fly straight out. They bump into particles again and again. They are absorbed and re-emitted. They change direction countless times. So the energy drifts outward very slowly. It is like trying to leave a crowded room by taking one small step, then another. You still make progress, but it is gentle and gradual. That slow drift happens in what is often called a radiation zone, a region where light carries energy outward through endless tiny interactions. Now, the other style is convection. Convection is energy carried by moving material. Warm material rises. Cooler material sinks. It is like warm bubbles in water, but the water is plasma. In convection, energy moves outward because the matter itself is moving. A parcel of hot gas rises, releases some energy, cools, and sinks again. This creates a rolling, circulating pattern. In many stars, convection happens near the surface. In some stars, convection can also happen deeper inside. For the Sun, there is a radiation zone in much of the interior and a convection zone closer to the surface. Again, keep it simple. Some energy drifts outward as light slowly wandering. Some energy rides outward on warm rising bubbles. Do you prefer the idea of drifting light or rising warm bubbles? No need to answer. Either image is fine for sleep. Gravity in, pressure out, balance found. Now, from far away, the surface of a star can look calm, but up close, it can be lively. The Sun's surface has patterns, like softly boiling texture. Those patterns are linked to convection. Hot material rises, cool material falls. The overall effect is steady, not chaotic. It is a gentle motion across a bright surface. Sometimes the Sun has darker spots called sunspots. They are not holes. They are regions where magnetic fields affect the surface. They look dark only because they are cooler than the surrounding area. And even cooler on the Sun is still very hot by everyday standards. Sunspots come and go in cycles. The Sun has a magnetic rhythm that changes over time, often discussed as about 11 years. We do not need the details tonight. Just know that even on the main sequence, a star can have slow cycles and surface patterns. And yet, the star remains steady overall. Gravity in, pressure out, balance found. Now we come to one of the most calming truths about stars. Fusion is both powerful and incredibly slow. It sounds like it should be fast. But inside a star like the Sun, a single proton can wait a very long time before it fuses. Many collisions do nothing. Most of the time, particles simply bounce and move on. Fusion requires just the right conditions. And in the Sun, those conditions exist, but the key reactions are rare. That rarity is a gift. It prevents the star from burning through its fuel too quickly. Instead, the Sun shines with patience. So how do we get so much light if each particle is so unhurried? Because there are so many particles. The core contains an enormous number of protons. Even if each one has a tiny chance of fusing in a given moment, the sheer crowd makes the total steady. It is like a stadium full of people quietly breathing. Any one breath is small, but together, the result is a constant, reliable flow. This is the true pace of fusion in a main sequence star. Slow per particle, steady in total. A calm engine, not a roaring one. And it produces light that travels outward for a long time before leaving the surface. By the time sunlight reaches you, it has had a long, wandering journey. Now, there are also quiet messengers that leave the core quickly. These are neutrinos. They are tiny particles produced in fusion reactions. They interact very weakly with matter, so most of them pass straight through the star and keep going. They are like soft whispers that slip out of the core with almost no delay. Neutrinos are difficult to detect, but we can catch a few with careful instruments on Earth. When we do, they confirm that fusion is really happening in the Sun's center. You can think of neutrinos as gentle proof that the core is working steadily. Quiet messengers from deep inside. We will soon talk about the specific fusion pathways. We will name the proton-proton chain and the carbon-nitrogen-oxygen cycle. No math, no hurry. Just a calm description of how hydrogen becomes helium in different kinds of stars. For now, it is enough to know the main sequence is powered by fusion in the core, and that the star regulates itself, staying stable for long spans of time. Gravity in, pressure out, balance found. Now let's talk about aging, but in a very soft way. Even in the main sequence, a star slowly changes. It does not stay perfectly the same forever. In a sun-like star, the core gradually uses up hydrogen. Not all at once, but steadily. As hydrogen becomes helium, the core's composition changes. Helium is heavier than hydrogen. As helium accumulates, the core can become a little denser. A denser core tends to contract slightly. Contraction raises temperature and pressure. That can make fusion run a little faster over time. So a star like the Sun slowly becomes brighter as it ages on the main sequence. This change is gentle. It happens over billions of years. It is not something that comes with a sudden shift in one night, but it is a real part of the story. The Sun was slightly dimmer when it was younger. It is slightly brighter now than it used to be. And it will become brighter still, very slowly, as it continues its main sequence life. This is one reason steady does not mean frozen. It means stable, self-correcting, and slow to change. The star is always adjusting to keep balance. Gravity in, pressure out, balance found. And the Sun has plenty of time left in this phase. It is middle-aged in a cosmic sense, but not near the end of its steady chapter. You can let that thought feel comforting. The Sun will keep rising and setting for a very long time, in human terms. Stars are reliable companions. Now, another soft reset, as promised. Nothing to do. Just listen. If the details are slipping away, that is fine. Let them drift. Hold onto one simple rhythm instead. Gravity in, pressure out, balance found. Now, picture a main sequence star from the outside. A bright sphere with a steady glow. It does not shine because it is burning like wood. It shines because deep inside, tiny changes in nuclei release energy. That energy finds its way outward through drifting light and moving material. The surface releases photons into space. Those photons travel outward, crossing the emptiness between stars. Some of them find a planet. Some of them warm a face. Some of them become the quiet light in a room. All of that begins in the core, in a balanced, steady engine. Now, if you want one more gentle image, think of the main sequence as a long plateau. Before it, the star was still assembling, still adjusting. After it, the star will eventually change shape as fuel runs low. But on the plateau, the star is at its most stable. This is the chapter where stars spend most of their time. This is why, when you look at the night sky, many of those points of light are main sequence stars. They are not all identical, but many are in that long, steady glow. Some are hotter and bluer. Some are cooler and redder. Some are brighter, some dimmer. Yet the underlying rhythm is shared. Fusion in the core, balance in the structure, light streaming outward. Gravity in, pressure out, balance found. We will return later to the moment when the core hydrogen runs low enough that the star gently changes its shape. That moment leads toward the red giant stage. For now, we stay in the steady middle, because understanding the main sequence makes the rest of the life cycle easier to hold. It is the baseline, the calm reference point. Now we can lean closer to the engine itself. We can look at fusion with a little more detail, still softly, still slowly. With that steady rhythm established, let's look closer at the calm engine itself. Fusion. We have a steady star. Now we can look gently at the engine inside it. Fusion is not a flame. It is a quiet set of nuclear steps, repeating endlessly in the core. In a main sequence star, the main job is simple in spirit. Hydrogen becomes helium. The details are where the calm beauty lies. In stars like the Sun, the most common pathway is called the proton-proton chain. You can think of it as a slow recipe with several stages. It is slow on purpose. Most collisions do not fuse, and the ones that do happen through rare, careful interactions. First, two protons meet. Very often they bounce apart, but once in a long while, one proton changes into a neutron. That change helps form a heavier nucleus called deuterium. Deuterium is like hydrogen with an extra neutron. When that change happens, two small particles are produced as bookkeeping. One is a neutrino, a quiet messenger that slips away almost instantly. The other is a positron, the antimatter partner of an electron. The positron does not travel far. It meets an electron nearby. When they meet, they turn into energy, mostly as light-like radiation. Even this is not a flash in the way we imagine fireworks. It is energy added to a crowded, hot environment spreading out gently. The newly formed deuterium then meets another proton. They join to make helium-3. Helium-3 is a light helium nucleus with two protons and one neutron. Then two helium-3 nuclei can meet. They join and rearrange into helium-4. Helium-4 is the stable helium most people think of. In that step, two extra protons are released back into the mix. They are returned to be used again later. So the overall result is that four protons become one helium-4 nucleus, and a small amount of mass becomes energy. The energy comes out in pieces, some as energetic light, some as motion of particles, some as heat. And it takes a long time to wander out of the star. The core is like a crowded hallway. Photons bump, turn, and bump again. So by the time energy reaches the surface, it has been softened into a steady glow. Nothing to do. Just listen. It can help to remember that fusion in the Sun is calm because it is slow. It is slow because the key step requires that proton to neutron change. That change involves what physicists call the weak interaction. You do not need the name. You only need the feeling. The universe allows it, but it does not rush it. That is why a sun-like star can shine for billions of years. It is not chewing through fuel quickly. It is sipping patiently. Now, not all stars use the same pathway in the same way. Hotter, more massive stars often rely more on a different process. This is called the carbon-nitrogen-oxygen cycle. You can shorten that to the CNO cycle, spoken as CNO. The CNO cycle is still hydrogen becoming helium. The difference is how it gets there. In this cycle, carbon, nitrogen, and oxygen act like helpers in a loop. They are not used up in the end. They assist the reactions, then return to their starting form. That is what a catalyst does. A catalyst helps a process happen more easily without being consumed. In the CNO cycle, a carbon nucleus captures a proton. It becomes a heavier form, then changes through steps. Along the way, it can become nitrogen, then oxygen, then back again. At certain points, a positron and a neutrino are released, just as in the proton-proton chain. And at the end of the loop, the catalyst returns and a helium nucleus has been made. The loop can continue again and again. Why does this matter more in hotter stars? Because the CNO cycle is very sensitive to temperature. As the core temperature rises, the cycle speeds up strongly. So, in a more massive star with a hotter, denser core, CNO can dominate the energy production. It becomes the main engine. In the Sun, the proton-proton chain is the main one. In heavier, hotter stars, CNO takes the lead. This difference connects directly to lifespan. A hotter engine burns through hydrogen faster. We will return to that soon when we compare stars by mass. For now, just keep the quiet contrast. The Sun uses a slow pathway. More massive stars have a faster pathway available. Still steady, still regulated, but faster overall. Nothing to do. Just listen. Now let's talk about the energy itself, gently. When 4 protons become one helium nucleus, the helium nucleus has slightly less mass than the 4 protons added together. That missing mass becomes energy. This is the idea behind the famous equation E equals meters c squared. You can say it as energy equals mass times the speed of light squared. The speed of light is enormous, so even a tiny mass difference becomes a lot of energy. But we do not need to dramatize it. Think of it as a small, constant conversion happening all the time, like a slow drip filling a lake. Any one drip is small, but the lake keeps rising steadily because the dripping never stops. In a star, the drip is the small mass difference in each fusion event. The lake is the total output of light and heat produced continuously. This is why stars can be both calm and powerful. Their power comes from patience plus scale. Countless reactions, each one tiny, spread over immense time. Now, there is a common misconception that fusion is like a fuel tank emptying abruptly. Stars do not behave that way. Fusion does not suddenly cut off like a lamp. It changes smoothly. Because fusion rates depend on temperature and pressure. And temperature and pressure are connected to a star's size and structure. If the core warms, fusion speeds up and pressure grows. The star expands a little and cools the core. If the core cools, fusion slows and gravity tightens gently. The star contracts a little and warms the core. So the star is always adjusting. Even its fuel use is regulated by its own balance. That means when hydrogen becomes less abundant in the core, the star does not suddenly go dark. Instead, the star slowly responds. The core may contract a little. The temperature may rise a little. The fusion rate may shift. The brightness can increase gradually. It is all smooth, like a long fade rather than a sudden stop. This is why we can speak of stellar evolution as chapters, not shocks. Even later, when a star changes into a red giant, the story is paced over long times. We will get there, but for now, the main point is that the engine is calm. It does not surge uncontrollably. It does not stall suddenly. It adjusts. Nothing to do. Just listen. Now, let's gently compare the 2 pathways again without rushing. The proton-proton chain is the Sun's quiet method. It is efficient at the Sun's core temperature. It proceeds through rare steps, which makes it naturally slow. The CNO cycle is another route to the same goal. It uses heavier nuclei as helpers, and it becomes much more important in hotter cores. Both produce helium from hydrogen. Both produce neutrinos as quiet messengers. Both release energy in small pieces that add up. Both are held steady by the star's internal balance. So when you look at a star, you are not seeing a fire. You are seeing the long-term outcome of microscopic, repeated nuclear bookkeeping. The star is like a calm accountant of energy, always balancing its books. Fusion adds pressure. Gravity demands pressure. The two meet in the middle. Now, here is a soothing thought about time. The light leaving a star's surface right now began as energy in the core long ago. In the dense interior, energy moves slowly outward. So there is a long delay between creation and release. That delay is another reason stars are steady. Even if the core changed slightly, the surface would not respond instantly. The star has thermal inertia, a kind of built-in smoothness. It is hard for it to behave abruptly. It prefers gradual change, just like we want tonight. Now, a single calming question, just to keep your mind gently engaged. Would you rather live slowly for trillions of years or brightly for a few million? No need to answer. You can let the question float by like a cloud, because that choice is, in a way, what stars face. Small stars sip their fuel and last a very long time. Large stars burn hot and live shorter lives. The engine pathway and the core temperature are part of why. And the biggest factor behind all of it is mass. Before we go there, one more soft clarification. Fusion turns on smoothly too. In a protostar, heating comes from infall and compression. As the core temperature climbs, fusion reactions become possible at a meaningful rate. They do not happen zero, then suddenly a flood. They ramp up. As fusion strengthens, it adds pressure support. That helps the star settle into main sequence balance. So the main sequence is not a switch. It is a settling, a gradual arrival at a stable rhythm. The engine becomes the primary support, and the star becomes long-lived. And when the core hydrogen begins to run lower, later on, the change is also gradual. The star adjusts again. So the full life cycle can be told without hype, because nature does not usually use hype. It uses feedback loops, slow flows, and time. Now that you know the engine, we can talk about the single biggest factor in a star's entire story: mass. Just a small, optional pause. If you want more calm science for nights like this, you can subscribe now. One gentle tap, and then let your hands relax again. No scrolling, no comments, no bright screens. If you are already drifting, skip this with silence. Your rest matters more than any button. And if you come back to this channel another night, the familiar voice and rhythm can become a simple signal, a cue that it is safe to soften your thoughts. All right, let your attention settle back into the story, like a blanket falling into place. Next, we will compare small stars and big stars and how time feels different for each. Now that you know the engine, we can talk about the biggest factor in a star's whole story. That factor is mass. Mass is the amount of material a star is born with, and it quietly decides almost everything that happens next. Here is a soft rule of thumb. More mass usually means much more brightness, not just a little more. Often a lot more. And that brightness is not free. A brighter star is using its fuel faster. So even though a massive star has more fuel to start with, it spends it at a quicker pace. This is why mass is such a good predictor of lifespan. Small star, long story. Big star, short chapter. You do not need to remember. Just let it pass. Think of a small campfire and a large bonfire. The bonfire has more wood, but it also burns hotter and faster. The small fire can last quietly through the night. Stars are not fires, but the comparison helps with intuition. Brightness is a sign of the rate of energy production, and energy production is tied to how quickly the core is fusing hydrogen. More mass means more gravity. More gravity means the core is squeezed more strongly. A squeezed core gets hotter and denser. A hotter core allows fusion to proceed more quickly. So mass sets the core conditions, and the core conditions set the pace. This is the mass luminosity idea in plain language. It is not a single exact formula you need to memorize. It is a direction. Heavier stars tend to be brighter. Brighter stars tend to live shorter lives. Small star, long story. Big star, short chapter. Now let's meet the quiet dwarfs. Red dwarfs are small stars, cooler and dimmer than the sun. They are the most common stars in our galaxy. They are easy to miss with the naked eye because they do not shine very brightly. But they are everywhere. If the Milky Way is a city, red dwarfs are the most common kind of home. Because they are small, they burn their fuel slowly. They can keep fusing hydrogen for a very long time. So long that we have to use a word that sounds almost unreal. Trillions of years. That is not a typo in your mind. It is simply a number far beyond human history. The universe itself is not old enough for the smallest red dwarfs to have reached old age. Many of them are still in their early or middle main sequence chapters, even if they formed long ago. When you look at a red dwarf, you are often seeing a star that will outlast many generations of galaxies changing shape. You do not need to carry that timescale precisely. Just let it widen your sense of time. A red dwarf is a slow lamp. It is dim, steady, and extremely patient. One reason red dwarfs last so long is that they can be very efficient with their fuel. In many red dwarfs, convection can mix material through much of the star. That mixing helps bring fresh hydrogen inward over time, so the star can use a larger fraction of its hydrogen supply. It does not rely only on a small, isolated core. It stirs itself gently, and that stirring extends its life. Again, no need to hold the details. Small star, long story. You do not need to remember. Just let it pass. Now move up the scale to stars like the sun. Sun-like stars live in a balanced middle. They are not the smallest and not the largest. They shine with a steady warmth. Their main sequence lifetimes are often described as around 10 billion years. That is a rounded number, but it is a good bedtime number. Long enough to feel stable. Short enough to feel like a chapter, not an eternity. Our sun is about 4.5 billion years old, so it is roughly partway through its main sequence phase, and it still has a long, steady stretch ahead. A sun-like star spends most of its life quietly fusing hydrogen in a core. It adjusts itself with that thermostat-like feedback. It changes slowly as helium builds up in the center. And over billions of years, it becomes gradually brighter. These are gentle changes, not sudden ones. In human terms, the sun's future is slow. Even the biggest changes in its far future unfold over timescales that make our calendars feel tiny. We will later visit the sun's red giant chapter. That transformation is real, but it is not a rush. Tonight, the main point is simply this. Sun-like stars are a calm middle case. They live for billions of years. They have long, stable phases, and their evolution is gradual. Small star, long story. Medium star, long chapter. You do not need to remember. Just let it pass. Now let's step up again to massive stars. Massive stars are bright, hot, and short-lived compared to the sun. Their cores are squeezed more strongly. That makes their core temperatures higher. And at higher temperatures, fusion pathways can change. This is where the carbon-nitrogen-oxygen cycle becomes more important. It can run much faster in hot cores, so massive stars convert hydrogen to helium at a quicker pace. They shine intensely, and they burn through their central hydrogen in a relatively short time. Their lifespans can be a few million years to tens of millions of years. That might still sound long, but in cosmic terms, it is brief. If a red dwarf is a slow candle, a massive star is a bright lantern that does not last as long. It is not unstable in the sense of flickering out randomly. It can be stable on the main sequence. It is just running its engine at a higher setting, so the fuel is consumed faster. Small star, long story. Big star, short chapter. You do not need to remember. Just let it pass. Now here is an important open loop, held gently. These short-lived massive stars are key to making many heavy elements. They reach higher temperatures later in life. they can fuse heavier nuclei in layers. And when they end, they can spread enriched material into space. That material becomes part of new clouds, new stars, and future planets. We will return to this when we talk about element creation and cosmic recycling. For now, just let it sit like a quiet promise. The bright, brief, lives matter for what comes next. Now, there is one more quiet modifier to add. It is called metallicity. In astronomy, the word metals means something different than in everyday speech. It means any element heavier than helium. So carbon is a metal in this sense. Oxygen is a metal. Iron is a metal. All of them. Hydrogen and helium are the light starting materials. Everything heavier is grouped as metals. Metallicity describes how much of that heavier material is present in a star. It is like the recipe seasoning. Most of the star is still hydrogen and helium, but small differences in heavier elements can affect how a star behaves. Why? Because heavier elements and dust can change how easily light moves through stellar material. They can change opacity, the star's tendency to block and absorb radiation. Higher opacity can trap energy more effectively. That can influence temperature gradients and convection. It can subtly shift where a star sits on that map of brightness and temperature. It can also affect winds and how mass is lost over time. These are fine details, and we will not go deep tonight. But the gentle takeaway is useful. Mass sets the broad story. Metallicity adjusts the tone of the story, like the same melody played in a slightly different room. Where do those metals come from? Not from the Big Bang in large amounts. They come from earlier generations of stars, stars that lived, fused, and returned material to space. So metallicity is like a family history. A star with more metals formed from a cloud already enriched by older stars. A star with fewer metals formed earlier from a more pristine mix. We will soon see how that enrichment happens, calmly through stellar life and death. For now, you can keep one idea. The universe learns chemistry over time. Each generation leaves quiet traces for the next. Small star, long story. Big star, short chapter. And composition, a gentle modifier. You do not need to remember. Just let it pass. Now, let's weave these threads together in one calm summary. A star's mass influences its gravity. Gravity sets the core's pressure and temperature. Core conditions set the fusion pace. Fusion pace sets brightness. Brightness sets how quickly the star uses its fuel. And that sets lifespan. It is like a chain of soft causes, each leading to the next. You do not need equations to feel it. Just a steady logic. Now imagine lining up 3 stars. A small red dwarf, dim and long-lived. A sun-like star, balanced and steady for billions of years. A massive star, bright and brief on a cosmic clock. All 3 can be main sequence stars. All 3 can be stable in their own way. They simply live at different tempos. Some stories are long and quiet. Some are short and luminous. Neither is better. They are different expressions of the same physics. Now, another rest line. You do not need to remember. Just let it pass. If your mind is trying to hold on to numbers, you can let them go. Keep only the feeling of scale. Trillions for the smallest stars. Billions for sun-like stars. Millions to tens of millions for the most massive stars. Those are rounded, gentle ranges. And the logic behind them is mass. Now, with mass in mind, the next big chapter becomes easier to understand. Because when the core hydrogen begins to run low, the star responds. It does not panic. It adjusts. For sun-like stars and larger ones, that adjustment often involves expansion. The outer layers swell outward. The surface cools. The star becomes a red giant, or for massive stars, a supergiant. That transformation is not sudden. It is the next slow change in shape, guided by the same balance between gravity and pressure. So, we will move there next. With mass in mind, we can drift into the next gentle transformation, a star expanding into a red giant. Now we move into a gentle transformation. The star begins to change shape when its core hydrogen runs low. It is not a sudden crisis. It is a slow adjustment, guided by the same balance we have been using all along. For most of a star's main sequence life, the core is the main factory. Hydrogen fuses into helium and pressure support stays steady. Over time, helium builds up in the center. Eventually, the central region has less hydrogen to fuse. When fusion slows in the core pressure drops a little. Gravity responds by tightening gently. The core contracts. And when a gas is compressed, it warms. So the core becomes smaller, denser, and hotter. This is the first key step in becoming a giant. Now the outer parts of the star respond. As the core contracts and heats, conditions change in a layer surrounding the core. Hydrogen in that surrounding layer can still fuse. In fact, it can fuse more actively now because the layer is warmed by the contracting core. So fusion continues, but not in the center. It continues in a shell around the core. This is called shell burning. And shell burning changes the star's structure. It adds energy to regions outside the core. That extra energy pushes outward on the star's outer layers. So the envelope expands. Picture the star breathing. Expand, pause, soften. As the envelope swells, the surface spreads out over a larger area. And when a surface area grows, the same energy can be spread more thinly. So the surface temperature drops. A cooler surface shifts the star's color toward red. This is why we call it a red giant. The star is not necessarily red like a stoplight. It is simply cooler than before, with a warmer, reddish tint. And it is much larger. This is a good moment to soften a word. The word giant sounds dramatic, but in astronomy, giant is mostly about size. It does not always mean the star has huge mass. A sun-like star can become a red giant. Even though it is not a massive star, it becomes large because its outer layers expand. So giant means expanded, not heavy. Does the word giant feel less dramatic now? No need to answer. Just let the meaning settle. Now, in this giant phase, the star can become brighter overall. Even though the surface is cooler, the surface area is much larger, so the total light output can increase. It is like a warm lantern growing a larger shade. The light becomes softer in color, but the lamp fills more space. A red giant can be luminous, yet gentle in temperature. If you are picturing it, imagine the star as a glowing ember wrapped in a huge, faintly glowing cloud. The core is compact and hot. The envelope is wide and cooler, and the boundary between them is where shell fusion is working steadily. Nothing to do. Just listen. Now, if the star is more massive, we use the word supergiant. Supergiants are even larger and more luminous. They are the expanded forms of massive stars as they evolve. But the calm logic is similar. Core fuel changes. The core contracts and heats. Fusion shifts into shells. The outer layers swell outward. In massive stars, the details become more layered later on with multiple shells. But for now, we can hold one shared image. A star becomes a bigger shape when its central fuel arrangement changes. It is a structural response, not a tantrum. Now, let's stay with shell burning for a moment because it is a new kind of steady. A main sequence star is steady because the core is fusing hydrogen. A giant is steady in a different way because a shell is fusing hydrogen around an inert core. When we say inert core here, we mean the core is not fusing hydrogen anymore. In a sun-like star at first, that core is mostly helium. It is hot and dense, but it is not yet fusing helium. So it sits there, contracting slowly, while the surrounding shell does the hydrogen fusion. That shell keeps adding helium ash onto the core. So the core grows in mass over time. And as it grows, it tends to compress further. This is a quiet feedback. Shell burning builds the core, and the core sets conditions for what happens next. Now, while this is happening, the star's outer layers can become more dynamic, not violent, but responsive. Red giants can pulsate. They can expand and contract slightly, like slow breathing. These pulsations can be regular or semi-regular. They are part of how the star settles into its changing structure. If you want a guided image, picture the star breathing again. Expand, pause, soften. The surface brightness can vary gently as it breathes, but the star remains a coherent, steady object. It is not falling apart all at once. It is adjusting on long timescales. Nothing to do. Just listen. Now we arrive at the next internal transition, helium ignition. This is where the story begins to connect directly to element creation, because when helium fuses, it can begin to build carbon. We will soon talk more about how stars create elements. For now, we introduce the calm idea. After enough time, the contracting helium core reaches conditions where helium fusion can begin. Helium nuclei are heavier and carry more electric charge than protons, so they resist coming together more strongly. That means helium fusion needs higher temperatures than hydrogen fusion. Eventually, the core gets hot enough. Then helium can begin to fuse into carbon through what is called the triple alpha process. The name sounds technical, but the idea is simple. An alpha particle is a helium nucleus. 3 helium nuclei can, through steps, combine into carbon. This is one of the quiet beginnings of carbon in the universe, and it happens deep inside evolved stars. Now, there is a phrase you may have heard, helium flash. It can sound intense. We can describe it gently. In some sun-like stars, the core becomes partially supported by a kind of pressure that does not depend much on temperature. That can allow helium to ignite in a rapid internal transition. But this happens inside the star, and the outer layers respond smoothly. From the outside, it is not an explosion you would see like a flare. It is an internal rearrangement, a change of regime. So you can treat helium flash as a name for a quick internal adjustment. It is the star finding a new balance. Nothing more you need to feel tonight. Once helium fusion begins, the star can settle into another steady phase. The core now produces energy from helium fusion. The outer shell may still burn hydrogen, so the star can have multiple energy sources at once. This can change its size and brightness again. It may shrink slightly compared to its most expanded giant state, then later expand again. The precise track depends on mass and composition, but the overall story remains calm. Fuel changes lead to structure changes. Structure changes lead to surface changes, and everything happens over long times. Nothing to do. Just listen. As helium fusion continues, carbon builds in the core. In some stars, carbon can also fuse later, but that requires even higher temperatures. Sun-like stars do not usually get hot enough in their cores to fuse carbon significantly. So for them, carbon and oxygen can become the final core products. The core becomes a carbon-oxygen core. And once the helium in the core runs low, the star shifts again. This brings us into the later giant stage, sometimes called the asymptotic giant branch. You do not need the label, just the feeling. Later giant, later shedding. In this later stage, the star can have helium shell burning and hydrogen shell burning in layers. The energy production can pulse in cycles. Again, not like sudden shocks, but like slow beats. Those beats can make the outer layers more loosely bound. And that leads to the next gentle part of the story, winds. Red giants and supergiants can lose mass through stellar winds. A wind in space is a flow of particles leaving the star. It can be slow and steady. In giants, the surface gravity is lower because the star is so expanded. So it is easier for the outer layers to drift away. Pulsations can help lift material outward. Radiation pressure on dust in the outer atmosphere can also help push matter away. The result is that the star slowly sheds its outer layers. Not all at once, over long times in a patient shedding. Picture a scarf slowly unraveling, thread by thread, or picture a dandelion losing seeds in a gentle breeze. The star is not being torn apart. It is simply letting go of its outer envelope. This mass loss is important for what comes next, because the core is left behind, and the outer layers become a drifting shell of gas and dust. We are keeping an open loop for the next section. Those drifting outer layers can become a planetary nebula, and the exposed core can become a white dwarf. For now, we hold the image of a giant in its late phase, a warm inner region, a large cool envelope, slow breathing pulses, and a faint wind carrying material outward into space. If the star is massive enough to become a supergiant, its winds can be strong too. Massive stars can shed a lot of material before they end, but we will speak about massive star endings later. Right now, we stay with the gentle common path. A sun-like star becomes a red giant, then sheds its outer layers and leaves behind a compact core. That core will cool in silence for a very long time. Before we go there, let's offer one more calming recap line. Core contracts, shell burns, envelope expands. Core contracts, shell burns, envelope expands. This is the basic rhythm that makes a giant. It is the star responding to a change in where fusion happens. And as it responds, its color shifts warmer, its size grows, and its light output can rise. All without hype, just physics. Unfolding slowly. Now we can let the giant phase fade. We can let the outer layers drift away, and we can arrive at one of the calmest endings in astronomy. As the giant phase fades, we arrive at one of the calmest endings, a white dwarf cooling in silence. Now the giant phase begins to let go. The outer layers drift outward and the star unwraps itself. This is one of the softest transformations in stellar life. We often see it as a planetary nebula surrounding a white dwarf. Let's start with the nebula. A planetary nebula is a beautiful name, but it is a bit misleading. It has nothing to do with planets. The name comes from history. Early observers using small telescopes saw round, planet-like disks. So the label stuck. Today we know it is a shell of gas released by a dying giant star. It is the star's outer atmosphere set free. Imagine a slow breath leaving the star and never returning. The gas expands outward into space. It is thin and delicate, like mist, and it spreads into a shape that can be round, oval, or softly lopsided. The shapes can be sculpted by winds, magnetic fields, and any companion stars nearby, but you do not need to chase every detail. Tonight we hold one simple picture, a fading shell, drifting outward, lit from within. The light source is the hot core left behind. After the giant sheds its envelope, the core is exposed. It is very hot at first. It sends out energetic light that can excite the surrounding gas. The gas responds by glowing softly in specific colors. In photos, those colors can be vivid. But in our calm telling, think of it as a faint lantern glow in a thin fog. Not bright like a lamp in your room, more like a quiet aura in the dark. A planetary nebula does not last very long in cosmic terms. It expands and thins out. Over time, it mixes into the surrounding interstellar medium. A common rounded timescale for its visible phase is on the order of 10,000 to 50,000 years. That is long by human standards, but for a star, it is a brief farewell. A final, gentle display before the gas becomes part of the galaxy again. If you want a soft image, picture ripples spreading on a dark pond. The ripples become wider and fainter. Eventually, they are hard to see at all. That is the planetary nebula's path. Nothing to do. Just listen. Now let's look at the core itself, the white dwarf. A white dwarf is what remains when a sun-like star can no longer sustain fusion. It is not a burning star anymore. It is a stellar ember, a dense, hot remnant. It contains a large fraction of the star's original mass. Often the mass is comparable to the sun's, or at least in the same neighborhood, but the size is far smaller. A typical white dwarf is closer to the size of Earth, so you have a sun-like mass packed into an Earth-like volume. That is a quiet kind of extreme. It does not explode. It simply exists, dense and compact. The pressure holding up a white dwarf is not ordinary gas pressure. It comes from quantum rules. The electrons inside the white dwarf are squeezed into a state where they resist being packed tighter. This resistance is called electron degeneracy pressure. You can think of it as a built-in firmness that appears when matter is compressed enough. It does not depend strongly on temperature. It depends on how tightly the electrons are packed. So even as the white dwarf cools, it remains supported. It does not collapse like a normal gas ball would. This is one of the moments where the universe shows a different kind of stability. Not a thermostat based on fusion, a stability based on the rules of quantum physics. Still, we can keep it simple. A white dwarf is held up by the crowding of electrons, like a room so full that no one can step closer. The structure becomes self-supporting. Now, because there is no longer steady fusion in the core, a white dwarf does not have a new energy source. It shines because it is hot from its past. It stores heat, and it slowly leaks that heat into space. So a white dwarf is a cooling object. Its light gradually fades over billions of years. It cools slowly because it is dense and has a lot of stored thermal energy, and because there is no big change demanding quick action. It is simply cooling steadily for a very long time. If you like bedtime imagery, think of a stone that was warmed by the sun all day. At night, it releases that warmth slowly. A white dwarf is a cosmic version of that, stretched over immense time. As it cools, it can change color. It may begin very hot and appear bluish white. Then it becomes less hot and its light becomes dimmer and redder. Eventually, it becomes so cool and faint that it is hard to detect. In the far future, a fully cooled white dwarf is sometimes called a black dwarf. That is a theoretical end state, because the universe is not old enough yet for any white dwarf to have cooled that far. So in our current cosmos, white dwarfs are still cooling, still glowing faintly. Again, patience is the theme. Nothing to do. Just listen. Now let's add one more quiet, interesting idea. Over very long times, the interior of a white dwarf can begin to crystallize. That means some of the matter can settle into a more ordered, solid-like state. This does not mean it becomes a simple rock with a hard surface you could stand on. It is a very dense, exotic form of matter. But the general idea is peaceful. As the white dwarf loses heat, it can gradually transition into a more crystalline interior. It is like a slow settling, a quiet organization of atoms deep inside. This process can release a bit of additional energy, like latent heat. And that can slightly slow the cooling at certain stages. Astronomers can infer aspects of this by looking at populations of white dwarfs and how bright they are. But again, we do not need the technical side tonight. We only need the mood. A white dwarf is not only cooling, it may also be slowly becoming more internally ordered. A calm crystallization over cosmic time. Now, a small teaser, kept gentle and brief. Some white dwarfs have companion stars. In close binary systems, a white dwarf can gain material from its companion. If it gains too much, it can eventually reach a critical point and undergo a Type Ia supernova. Those events are important in astronomy because they can serve as standard candles to measure cosmic distances. We will not go deep into that here. It belongs more to the story of explosive endings, and tonight we keep our tone soft. For now, it is enough to know that most white dwarfs simply cool quietly, and a smaller number in special paired systems can have more dramatic futures. We will treat those futures calmly later if they appear. Nothing to do. Just listen. Now, let's bring this home to our own star. The sun's likely path is in this gentle category. It will spend a long time on the main sequence. Later, it will expand into a red giant. Then it will shed its outer layers gradually. Those layers will drift out and glow for a while as a planetary nebula. And the core left behind will be a white dwarf. There is no sudden ending where the sun turns off overnight. Its changes are slow compared to human time. Even the shedding of its envelope is a process measured in long spans. So the sun's story, in its final chapters, is mostly a slow transformation, a gentle unwrapping. Now, Remember the open loop from earlier? We said we would connect star evolution to the matter in us. Here is part of that connection. In a sun-like star, helium fusion can build carbon. And along with carbon, oxygen can also be produced in later stages of helium burning. Those elements can remain in the core and also be mixed into the star's outer layers in some cases. When the star sheds its envelope, that ejected material can carry carbon and oxygen into space. Over long times, that enriched gas can become part of new clouds. Those clouds can form new stars and new planets. So the gentle unwrapping is also a gentle donation. A star returns material to the galaxy, and the galaxy uses that material again. The planetary nebula fades, but the atoms do not disappear. They drift into the interstellar medium. They mix with other gas. They become part of the next cycle. This is cosmic recycling in its calmest form. A white dwarf at the center cools quietly. A nebula around it expands and fades. And the story of the atoms continues elsewhere. If you want a single image to carry forward, make it this. A small bright pearl at the center, the white dwarf. Around it, a thin, glowing shell slowly expanding. Over time, the shell becomes wider and fainter. The pearl remains, cooling, steady, silent. No rush, no drama, just time. Now, we are about to visit a different ending. It is rarer, and it belongs to massive stars. Before we do, a quiet reassurance. We will talk about bright finales calmly. No sharp words, just simple steps. That's the quiet ending for many stars. Now we'll visit the rarer path for massive stars, described softly. We are going to visit the rarer ending for massive stars. We will keep it calm and simple, with soft words and steady pacing. A massive star lives fast compared to the sun. Near the end, it becomes layered inside, like a quiet onion. Each layer is a region where a different kind of fusion can happen. Hydrogen may still fuse in an outer shell. Helium can fuse in a shell beneath that. Deeper still, carbon and oxygen can fuse in their own zones. Then neon and silicon can appear as later fuels in hotter inner shells. These are not separate stars inside one star. They are layers of one star, each finding the temperature it needs. The star becomes a stack of gentle factories, one inside another. As the star ages, each new fuel stage tends to be shorter than the last. Not because the star is frantic, because heavier fusion steps require higher temperatures and proceed more quickly. So the pace of change increases as you move inward. Still, we do not need to chase exact timelines tonight. We only need the shape of the story. Layers build, fuel shifts, and the core grows heavier. And then it settles. At the very center, the star is building an iron-rich core. Iron is a turning point in stellar life. Fusion up to iron can release energy in many cases. But fusion beyond iron does not give the star extra energy to support itself. It costs energy instead of paying energy back. So iron is like a quiet limit sign in nuclear physics. Not a dramatic wall, just a change in the rules. When the core becomes too iron-rich, the star loses an important source of support. The core is still squeezed by enormous gravity, but it can no longer easily earn new pressure from fusion. So the core begins to change quickly. And then it settles. Now imagine the layered star again. Outside, shells still fuse and glow. Inside, the iron core is growing denser and more compact. At first, it is supported partly by pressure from packed electrons. But as the core mass rises, even that support becomes strained. The core approaches a point where it cannot hold its size. When support fails, gravity pulls the core inward rapidly. This is called core collapse. We will keep it gentle. It is the star's center compressing into a much smaller volume. The collapse happens quickly compared to the star's lifetime, but we can still describe it as a brief transition, not a spectacle. Matter falls inward, the density rises, and the core stiffens. At very high density, the core resists further compression strongly. It can rebound slightly, like a soft spring finding its limit. That rebound can help launch an outward wave through the star. And then it settles. This outward wave moves into the surrounding layers. It carries energy and momentum outward. In many cases, it becomes the start of a supernova. A supernova is a brief, bright finale in the life of a massive star. It is not the star burning in air. It is the star structure changing rapidly and shedding its outer layers. You can picture it as a sudden bloom of light and expanding gas. Bright, yes, but not angry. More like a luminous flower opening in the dark. And then it settles. There is another quiet player here, neutrinos. During core collapse, enormous numbers of neutrinos are produced. They carry away a large share of the energy. Most neutrinos pass through matter easily. They slip out of the core like countless tiny messengers. For a moment, the star becomes a source of neutrinos even more than light. We cannot feel them, and we rarely notice them, but they are part of how the collapse and the outward wave are shaped. Some of their energy can be absorbed in the surrounding material. That can help the outward wave keep moving. So neutrinos are not just bystanders. They are quiet carriers, helping the finale unfold. And then it settles. After the outward bloom, what remains depends on mass. If the core that is left behind is not too massive, it becomes a neutron star. If it is more massive, it can become a black hole. The outer layers that were shed become an expanding remnant. That remnant carries newly made elements into space. We will talk about those elements soon. For now, we keep the sequence simple. Layered star, iron core, collapse, outward bloom, compact remnant. And then it settles. Now, let's rest with the idea of a neutron star. A neutron star is the dense remnant left behind by many core collapse supernovas. It is small in size, but large in mass. People often compare its size to a city. That is only a comparison for scale, not a reason to feel uneasy. It is simply a compact object, a tiny dot by stellar standards. Inside, matter is compressed so strongly that many electrons and protons combine into neutrons. That is why it is called a neutron star. It is supported by the behavior of matter at extreme density. Again, the universe finds a new kind of stability, not by fusion, but by the firmness of densely packed matter. And then it settles. Neutron stars can rotate. They often rotate quickly because the collapsing core conserved its spin. When a large object shrinks, its rotation can speed up, so the remnant can become a fast spinner. Neutron stars can also have strong magnetic fields. In some cases, the magnetic field is especially intense. Those are sometimes called magnetars. You can think of a magnetar as a strong field cousin of a neutron star. Same family, different strength of magnetic character. We do not need to dwell on extremes tonight. Just know the family is varied. And then it settles. Some neutron stars become pulsars. A pulsar is a rotating neutron star whose magnetic poles emit beams of radiation. As the star spins, the beams sweep across space like a lighthouse. If one of those beams crosses Earth, we detect a pulse. Pulse after pulse, steady and precise. That regularity can be very soothing to imagine. A pulsar can behave like a cosmic metronome. Tick, pause, tick, pause. Not because it is trying, because its rotation is stable. Would you rather be a quiet white dwarf or a steady pulsar clock? No need to answer. Let the question drift by like a cloud. And then it settles. Pulsars are useful to astronomers because they keep time so well. Their pulses can be measured with great precision. Over long periods, their spin can slow gradually. That slowing is another calm change, not a sudden one. A neutron star, even while rotating fast, is still an object finding balance. It can cool over time. It can emit radiation and particles from its magnetic environment, but it remains compact and stable. It becomes a small, persistent presence in space, and then it settles. Now let's turn to black holes calmly. A black hole can form when the remaining core is massive enough that even neutron star support is not enough. Gravity compresses the core beyond the point where light can easily escape. A boundary forms around it. That boundary is called the event horizon. You can think of the event horizon as a one-way edge. Outside it, space behaves in familiar ways. Inside it, paths lead inward and do not return. This is not a monster in space. It is a region defined by gravity. And then it settles. There is a common myth that black holes are vacuum cleaners. They are not. Far from a black hole, gravity behaves like the gravity of any other object with the same mass. If our sun were replaced by a black hole of the same mass, the planets would still orbit in nearly the same way. They would not suddenly be pulled in. The key difference would be that there would be no sunlight. So the myth is worth gently releasing. Black holes do not reach out and grab everything. They influence their surroundings through gravity, like other massive objects do. Only very close to the event horizon do the differences become extreme. And then it settles. In some massive star endings, not all the outer layers are expelled. Some material can fall back inward after the initial outward wave. That fallback can add mass to the compact remnant. Sometimes that pushes the remnant toward becoming a black hole. Again, we can hold this as a soft adjustment. Matter moves, some escapes, some returns. The final remnant is what the mass allows. And then it settles. Whether the remnant is a neutron star or a black hole, the supernova remnant expands outward. It carries gas enriched with heavier elements. It also stirs the surrounding interstellar medium. Over time, that stirred gas can cool and gather again into new clouds. Those clouds can form new stars, and later, new planets. So even the bright finale is also a kind of giving back. A return of material to the galaxy. And then it settles. Now let's revisit the onion picture one more time, gently. In massive stars, shell after shell builds heavier nuclei. Hydrogen to helium, helium to carbon and oxygen, carbon and oxygen to heavier products. In later stages, silicon fusion helps build iron group nuclei. The star is like a layered workshop, refining matter step by step. When iron dominates the core, the workshop can no longer pay for its own support. So the core collapses and the outer parts are released. The event is brief compared to the star's life, but the consequences last for a long time. And then it settles. A calm way to picture this is as a story of support. During most of a star's life, pressure support comes from heat produced by fusion. Near the end, the core becomes too iron-rich to keep producing that heat profitably. Support weakens. Gravity compresses. New forms of matter support take over for the remnant. A neutron star is supported by dense matter rules. A black hole is a region where collapse continues past a boundary. Each is a stable outcome under different conditions. And then it settles. If you are listening and the words collapse or black hole feel too heavy, you can soften them. Replace collapse with compression. Replace black hole with a quiet boundary in space. The physics remains the same, but the feeling becomes gentler. This is a bedtime story about nature's long processes. Not a warning, not a thrill ride. Just the universe doing what it does. And then it settles. Now, a small retention reset in one line. Massive star, layered core, brief bright finale, compact remnant. Massive star, layered core, brief bright finale, compact remnant. You do not need to remember details. Let the rhythm carry you instead. And then it settles. There is also a peaceful detail about time here. Even though the finale is brief, it happens after a long buildup. A massive star spent millions of years shining steadily. It spent most of that time in the main sequence phase. Then it moved through advanced stages more quickly. So the supernova is the final punctuation mark, not the whole sentence. The sentence was long and steady. And then it settles. In the aftermath, a neutron star can continue as a precise clock. A black hole can sit quietly, influencing nearby space. The remnant gas can expand and cool. Over centuries and millennia, it becomes part of the galaxy's breathable material. The bright moment passes. The slow cycles continue. And then it settles. Now we can connect this to the next soothing thought. These endings are not only endings. They are a way the galaxy becomes richer in elements. They seed future star-forming clouds with heavier atoms. They help create the ingredients for rocky planets. They help create the ingredients for chemistry. And soon we will talk about those ingredients directly. Now, the most soothing thought of all. The elements in your body were patiently made in these long stellar stories. Just a gentle pause, and then we will continue. If you are still awake, you can leave one star emoji in the comments. Just one symbol, and then let your eyes rest again. No typing, no explaining, no extra thought. If you are already sleepy, do nothing at all. Silence is perfect. You can even let the phone face down and keep listening. I use small signals like that to know what helps people settle. And it also reminds the channel to keep making calm, slow science like this. All right, let your attention soften again like a curtain closing. And now we close the loop. How stars make the periodic table, slowly, step by step. Now we close the loop. We come to element creation and cosmic recycling. This is the quiet answer to why we say we are made of star stuff. We will move slowly, step by step, like a calm chemistry lesson in the dark. Let's begin with the simplest beginning. The early universe was mostly hydrogen and helium. Those two elements were the main starting materials. A small amount of lithium also formed early, but in much smaller quantities. So for a long time, the cosmos was simple. Mostly light atoms spread thin across expanding space. Then stars formed, and complexity began to grow. Stars are nature's slow chemistry lab. They take simple ingredients and over a long time, rearrange them. They do it without intention, just by temperature, pressure, and patience. You do not need to remember every pathway. Just hold the idea that stars are where complexity becomes possible. Now we can resolve one earlier open loop. We mentioned disks and planets. The raw ingredients of rocky worlds are the heavier elements, the metals in astronomy language. Those metals are not made in large amounts in the early universe. They are mostly made inside stars and spread outward. So the story of planets is tied to the story of stellar recycling. Old stars enrich clouds. Enriched clouds form new stars with disks. Disks can grow dust grains into larger bodies, and those bodies can become planets. That is one of the quiet cycles of the galaxy. Now let's focus on one element that matters for life as we know it: carbon. Carbon is a turning point for complex chemistry. It forms stable chains and rings. It can make a wide range of molecules. So when carbon appears in the universe, the chemical vocabulary becomes much larger. How does carbon form inside stars? One key pathway is the triple alpha process. We introduced it earlier in the Red Giant chapter. Here is the calm version again. In a hot, dense helium-burning core, helium nuclei can combine. A helium nucleus is sometimes called an alpha particle. Two helium nuclei can meet and briefly form beryllium. That beryllium is unstable, and it would usually fall apart quickly. But in the dense, hot conditions of a giant star, another helium nucleus can arrive in time. Then the three together can become carbon. That is the triple alpha pathway. 3 helium nuclei become 1 carbon nucleus. It is a quiet act of assembly inside a star. No one sees it directly, but it changes the universe's inventory. Carbon is a quiet ancestor of many molecules we care about. Not because it was made for us, simply because it is a stable building block that stars can produce. Now, carbon does not always stay alone. In many helium-burning environments, carbon can capture another helium nucleus. That can produce oxygen. So oxygen is often made alongside carbon in evolved stars. This is part of how a sun-like star can build a carbon-oxygen core before it becomes a white dwarf. And it is part of how the universe becomes richer in oxygen over time. Oxygen becomes part of water, rocks, and the air of some planets. Again, not as a goal, just as an outcome of stellar interiors doing steady work. Now we can resolve another open loop. We said massive stars go further. They can reach higher temperatures and fuse heavier elements in shells. That is true. In sun-like stars, the core does not usually get hot enough to fuse carbon into heavier things in large amounts. So their element making reaches a kind of gentle limit. They produce helium from hydrogen. Later, they can produce carbon and oxygen from helium. Then they shed some of that enriched material through winds and planetary nebulae. Massive stars are different. They have hotter cores and more pressure. They can proceed to later stages. After helium burning, they can ignite carbon in the core. Then neon. Then oxygen. Then silicon. Each stage tends to be shorter than the previous one, but each stage adds to the layered structure of elements inside the star. This is like a quiet staircase. Hydrogen, then helium, then carbon and oxygen, then heavier products in deeper layers. The heavier the element, the rarer and more story-filled it tends to be, because it requires more extreme conditions, which fewer stars can provide. Now we can resolve the open loop about iron. In massive stars, fusion can build elements up toward iron, but iron is a turning point. Fusing iron into heavier elements does not release energy. So, a massive star cannot keep supporting itself by fusing beyond iron in the same way. That is why the end stage involves core collapse and a supernova, and that supernova can spread the star's layered elements into space. So iron is both an element and a signpost. It marks a limit for energy-producing fusion in stellar cores. Now, a soft reminder. You do not need to remember, just let it pass. If the names of elements feel like too much, hold only the direction. Small stars go some distance. Massive stars go farther. And the galaxy becomes richer in ingredients over time. Now we come to a different way elements can be built, not by fusing light nuclei into heavier ones in the usual sense, but by adding neutrons to existing nuclei. This is called neutron capture. There are two broad styles, slow and rapid. We will treat them gently. First, the slow process. It is often called the S process, meaning slow neutron capture. This tends to happen in aging giant stars, especially in the later giant phase called the asymptotic giant branch. You do not need the label. Just picture an older giant with layered shells and a rich interior. In certain conditions, these stars can produce free neutrons. Those neutrons can be captured by nuclei like iron and its neighbors. When a nucleus captures a neutron, it becomes a heavier isotope. Sometimes that isotope is unstable. If neutron captures are slow enough, the nucleus has time to undergo beta decay between captures. Beta decay is a transformation where a neutron can turn into a proton with a neutrino released. The details are not needed tonight. The feeling is enough. Slow additions, patient rearrangements. A nucleus gains a neutron. Then, if it needs to, it changes internally, becoming a slightly different element. Then it can capture another neutron later. Step by step, over long periods, this process can build many elements heavier than iron. Not all of them, but many. It is like adding beads to a string one at a time with pauses between additions. A calm assembly line. And because it happens in giant stars, the products can be mixed into outer layers and later released by stellar winds. So old giants are not only shedding gas, they are shedding enriched gas. They are feeding the interstellar medium with heavier elements made by slow, patient pathways. Now we come to the rapid process. This is called the R process, meaning rapid neutron capture. Here the story involves rare conditions. Conditions where many neutrons are available at once. So many that nuclei can capture neutrons rapidly, faster than they can decay. This can push nuclei into very neutron-rich forms. Later, as the environment settles, those nuclei can decay towards stable, heavy elements. This pathway is associated with some of the heaviest elements we find, including gold and platinum. We can frame these as rare outcomes of rare moments, not because they are mystical, because the needed neutron-rich conditions are uncommon. Now we should be careful and calm about where the raw process happens. Astronomy has strong evidence that neutron star mergers are an important site for process elements. When two neutron stars merge, extremely neutron-rich matter can be ejected. That ejected matter can produce heavy elements as it expands and cools. We also think some explosive stellar events may contribute as well. There is active research about the relative contributions of different sites, so we can keep our wording gentle. Neutron star mergers are a leading candidate and likely a major one. Some kinds of supernovas may also play a role, depending on the details of the explosion. We do not need to settle the debate tonight. We only need the calm takeaway. The heaviest elements often require rare, neutron-rich environments. And those environments can occur when compact objects interact or when certain massive stars end. Now we can resolve another open loop. We said massive star-ending seed galaxies with heavy elements. They do through supernova remnants and winds. Neutron star mergers can also enrich space, sometimes in dramatic bursts, but spread across the galaxy over time. So the galaxy's chemical richness is built from multiple contributions. Slow winds from giants, fast events from massive stars, and compact object interactions. All of it mixing into the interstellar medium. Now, recycling. Recycling is the quiet way these elements get used again. When stars lose mass in winds or shed envelopes into planetary nebulae or explode and spread remnants, the material does not disappear. It becomes part of the gas and dust between stars. Over time, that gas and dust can cool and gather into molecular clouds again. And we are back at the beginning. Nebulae become the next cradles. This is where the metals become important. Metals are the raw ingredients of rocky worlds. Silicates and oxides form dust grains. Carbon-rich grains form other kinds of dust. These grains can help clouds cool and collapse, and they can later clump in disks. So chemical enrichment does not just decorate the universe. It changes what can form. A metal-poor cloud tends to form stars with different properties than a metal-rich cloud. A metal-rich cloud can form more dust. More dust can help cool the cloud. And more dust can provide more solid material in disks. So enrichment influences the next generation in subtle ways. This resolves our earlier metallicity modifier. It is the fingerprint of previous generations of stars. Now, a soft bridge back to you. The calcium in your bones is an element heavier than helium. Calcium is made in the later stages of massive stars and spread out when they end. The iron in your blood was forged in stellar interiors and scattered into space by violent, or at least energetic events in the distant past. The oxygen you breathe was made in stars that lived and died before the sun formed. Those atoms traveled through space. They joined clouds. They formed planets. They became part of chemistry and part of you. You are not separate from the cosmos. You are one temporary arrangement of its recycled materials. This is not meant to feel intense. It can be comforting. Your body is made of ancient travelers resting here for a while. Now, as promised, we will do a sleepy second pass, the whole life cycle, in one slow breath. Nebula, to protostar, to main sequence, to giant, to white dwarf, or to a compact remnant. Then enrichment, then a new nebula. Let's say it again, slower the second time. Nebula, to protostar, to main sequence, to giant, to white dwarf, or to a compact remnant, then enrichment, then a new nebula. You do not need to remember. You only need to let the order become familiar. Familiar order is soothing. It gives the mind a rail to slide along. Now we can connect the final loops gently. Disk to planets. The dust in disks is made of recycled elements. KNO to lifespan. Hotter cores run faster, so massive stars live shorter. Iron to end stages. Iron marks a limit for energy-producing fusion in cores. Metals to new worlds. Enriched gas makes rocky planets possible. All of these are parts of one long cycle. A cycle that does not rush. A cycle that repeats across the galaxy. Now, one more calm image to hold as you drift. Picture a cloud of gas and dust, dark and cool. Inside it, a small warm core forms. A disk appears and a star begins to shine steadily. For a long time, it is stable. Then it expands and changes shape. It sheds material or ends more dramatically if it is massive. That material becomes a faint mist between stars. Later, the mist gathers again, and new stars begin in the same quiet way. This is cosmic recycling. It is the universe keeping a slow inventory, using the same atoms in new arrangements. And somewhere in that cycle, the atoms that make you appear for a while then move on. That thought can be used as a gentle release. You do not have to hold everything tightly. Even your worries are temporary arrangements of energy and attention. You can let them loosen and let your mind settle. Now, we will let these facts settle into a final, quiet summary. Short, simple, and calm. If you want another calm science sleep, choose one video from the end screen and then let your hands rest again. No searching, no decisions beyond that. I'll meet you there on the next quiet night. For now, keep the volume low and let your thoughts drift. Good night.